Hello, my name is Benji Smith. I'm from Onslow College and I'm presenting problem number 2, Kelvin's dropper. The problem states, construct a Kelvin's dropper, measure the highest voltage it can produce, investigate its dependence on relevant parameters. This is Lord Kelvin's dropper. This is the original drawing he made of it. An important concept for understanding Kelvin's dropper is charge. Charge is a property of protons and electrons where like charges repel and unlike charges attract. Voltage is the difference in electrical potential energy divided by the amount of charge. A capacitor is two conductors separated by an insulator, which stores energy in the form of separation of charge. Charge attraction between the unlike charges keeps them on the capacitor, and capacitance is the increase in charge per unit increase in voltage. This is important because the two parts of the Kelvin's dropper act like a capacitor, as they each store charge, which creates a potential voltage across them. Another important concept is the ions in water. So water has several ions in it, such as H+, OH-, and H3O+. Normally there are approximately equal numbers of positive and negative ions, so the water is overall approximately neutral, and the charge stored by the Kelvin's dropper are these ions. So the Kelvin's dropper has four main parts: the water reservoir at the top, which is connected to two water droppers. These let out a stream of water which then splits into droplets. The stream of water passes through two rings which are connected diagonally to collectors. The rings and collectors are conductive and there are wires connecting them. So the theory behind this, so say there is an initial imbalance of charge, so in this case there is a positively charged water droplet on the left. When this falls, it will then make the left-hand collector positively charged, and that through the wire will charge the right-hand ring. This right-hand ring will then attract negative ions into the right-hand stream, which will form a droplet, which will fall and make the right-hand collector negatively charged. This will then make the left-hand ring negatively charged, and this process continues to occur with more and more charge getting accumulated in each part. The phenomenon still occurs, just the opposite way around if that initial droplet was negative, or these were started the other way around, so the left-hand collector was negative and the right-hand collector was positive. The two parts of the system form a capacitor because they are connected and have their charge difference. These droplets are formed due to plateau-Rayleigh instability, where small perturbations form in the stream, as you can see, and then due to the surface tension force being larger, where the diameter is smaller, the stream then splits into droplets. Voltage between the two parts of the system does not keep rising forever due to several effects that limit it. First of these effects is corona discharge, where objects that have a very high charge, such as the two parts of the Kelvin's dropper, will create an ionization region around them, where the air is ionized into positive and negative ions, and the unlike ions are attracted, which decreases the net charge of the object, while the like charges are repelled. Second of these is droplet repulsion, so when a droplet is falling, in this case towards the right-hand side of this ring and collector, there's a weight force, there's also an attraction force to the ring above it, and a repulsion force from the collector below it. These three forces add to give a net force downwards and to the right, which causes the droplet to accelerate downwards and out to the right. This causes the droplets to not land in the collector, and so they don't transfer the charge to the collector and therefore the ring. An example of this is here, where you can see off to the right the droplets spraying outwards and not landing in the collector. The third stopping effect is parasitic resistance, where there is effectively a very large resistor between the two parts that allows some charge to flow when there's a very large potential voltage. Note that this current does not have to be very large, as there is not much charge actually stored in these. So this is my experimental setup. There's a water reservoir at the top that I would fill up with a certain amount of water. There's then water droppers, the rings and the collectors. So when I perform the experiment, I would let the reservoir run until empty. The frame is made of PVC, so it's an insulator and doesn't allow much charge to flow. And the rings and collectors are conductive metal cans. So I used a custom circuit to measure the voltage of the Kelvin's dropper. So there's the effective capacitor of the Kelvin's dropper between the two parts, and because we don't know which way around the voltage is on this capacitor, we needed to use a full bridge rectifier in order to make it positive. When the switch is closed, some of the charge in the Kelvin's dropper capacitor goes into the measurement capacitor, and because the measurement capacitor is much larger than the Kelvin's dropper capacitor, it lowers the voltage to a measurable level, which was about 10 volts. We then attached an oscilloscope to measure the highest voltage produced. This is an example of what the oscilloscope measures, and I'm looking at the maximum voltage, which is circled. The parameters I tested were total height, relative position of ring and jet breakup, volume of water, and the ion concentration. For the total height, I measured this as the distance between the water dropper and the bottom of the collector. So I predicted that increasing the total height will decrease the maximum voltage, as there is a greater distance for the droplets to be able to fall outside the collector. We can see that there's no real trend here, so changing the total height does not significantly change the maximum voltage. Next is relative position of ring and jet breakup. So this is the distance between the center of the ring and the point at which the stream breaks into individual droplets, and this point was the same for both streams. So I predicted that increasing the relative position of ring and jet breakup will decrease the maximum voltage, as there's less attraction between the ring and the point where the stream splits into droplets. We can see that there is a downwards trend, so increasing the relative position of ring and jet breakup will decrease the maximum voltage. Next is volume of water. So this is the volume of water in the reservoir at the start of the test. I predicted that increasing the volume of water will increase the maximum voltage, but then after a certain point it will stay the same. We can see that this is true, and that the maximum voltage plateaus after 250 milliliters. Finally is ion concentration. So I predicted that increasing the ion concentration will make the maximum voltage stay the same, as adding more, because water already has a large number of ions, adding more available ions doesn't increase the maximum voltage. We can see that this is true. In conclusion, if there's an initial imbalance of charge, say a positively charged water droplet on the left, this causes the left-hand collector to become positively charged, which then causes the right-hand ring to become positively charged, which attracts negative ions, making the right-hand collector negatively charged, so the left-hand ring. This continues to occur, and more charge gets accumulated. For the parameters, there was no change for the total height and salt, and for the maximum voltage, you want a low relative position of ring and jet breakup and a high volume of water. These are my acknowledgements, my references. Thank you.